Welcome to the linear regression video. So here we have on the first slide a couple of the need to know things for this essential skill. Let's go ahead and take a moment, read them to yourselves, and we're going to go ahead and focus on those in the next couple of slides. Okay, moving on to our first topic. Here I've got some stuff written already out for us, and you'll notice on the left hand side I have two graphs. The first graph is going to be the scatter plot itself. Notice the red diagonal line going through it. That's going to be our line of best fit. So that's the top graph. And then the bottom graph here, you'll see on the left-hand side on the y-axis, it's identified as residuals. So this is our residual graph. And then on a residual graph, you're going to see a horizontal line. So that's going to be kind of like the behavior of our y-axis. All right, so we'll go ahead and we've got some content here, which we know context is extremely important in statistics because otherwise they're just numbers and we don't know what those numbers represent. So the information that we have here is about the nicotine and the tar content inside of cigarettes. So is nicotine content of a cigarette related to the tars in the cigarette? A collection of data in milligrams on 29 cigarettes produced the scatterplot, residual plot, and regression analysis shown. So our regression analysis is going to be our line of best fit right there, which I just highlighted in yellow. We know that it is the line of best fit because it's got the little hat on top of the Y. So we want to be able to extract both slope and y-intercept here. So I'm just going to go ahead and take a look over at the side here. And I know that the coefficient on the x, so this 0.065, that is going to be my slope. And I know that the constant, the 0.154, that is going to be my y-intercept. So what I'm going to do, I'm going to describe the slope in context, and then I'm going to describe the y-intercept in context. And then one of the things that we definitely focus on in statistics when it comes to y-intercept is, well, does the y-intercept actually make sense in the situation? And sometimes it doesn't, which is totally okay. It's actually pretty common that it doesn't. It's just a good starting place for us, but contextually speaking, might not really make much sense for this situation. So describe the slope in context. What we're going to do is, we know that slope is rise over run. So this slope value over here, this 0.065, if I want to think about it as a fraction, I would put a 1 underneath it. So the rise, or the y value, would be 0.065, and the run would be 1. So rise is 0.065, run is 1. And there are many ways to describe this, but if you take a look back at the notes, we went ahead and gave you kind of a framework for this. So I'm going to go ahead and pause the video, which would be really good for you to do right now, and I'm just going to write down like the generic version of it and leave blanks where I'm going to kind of fill some stuff in. So here I've set up the bones of the statement that we're going to write for slope and context. So for every 1 unit increase in, so the x variable, so this is us describing the run. So at this point, I would say that my x variable, I can just look at the x-axis, is going to be tar. And I'm going to go ahead and put the units here too, so in milligrams. So I'm just pulling it off the x-axis. The predicted, so this is the little hat guy, y variable, do the same thing, look at the y-axis. Looks like nicotine. Also in milligrams, so I'm just going to go ahead and put my units as I go. Okay, the increase-decrease comes from whether or not the sign on the slope is positive or negative. And that 0.065 is positive. So if it's positive, then we're going to say it will increase. And then all right, now I just grabbed the slope from the equation, which in this case was 0.065. And then I don't really need to worry about replacing the units with the appropriate measure because I've already identified milligrams for the x variable and milligrams for the y variable. So as long as I put the units in there, it should be good. And that's my answer to the first one. Now, do the same things, pause right now. I'm going to go ahead and write in the bones for the y-intercept statement directly from our notes on page 13, and then we can go ahead and fill in this stuff where it belongs. Okay, so I went ahead and I filled in the bones for the statement here. And remember, the y-intercept has to do with when the x value is 0. So whenever the x variable is 0, we want to know what's happening with the y variable. So I went ahead and just put the bones in here, so I'm going to add some stuff in. So when the x variable, again, I'm looking back up at the scatter plot, so the diagonal red line, so the line of best fit. So my x variable is still tar in milligrams, and I'm just going to go ahead and do the same thing. I'm going to put the units in there. Is 0. The predicted y variable, okay, y variable here was nicotine, which is also in milligrams. Okay, will be, all right, let's go back to the equation where the y-intercept is, and that was 0.145 units. All right, so now if I want to go ahead and think about this in the context of the question, this is basically saying when there is no tar in the cigarette at all, then we would say that the predicted nicotine is 0.154. Does that make sense in this situation? Well, it may or may not. I would definitely say that I don't think this makes any sense. If there is no tar in the cigarette, which actually is a common component of cigarettes, then I would expect if there's no tar, I don't expect there to be any nicotine either. So since they do kind of go hand in hand with each other. So I would say, I really don't think so. So no. If there is no tar, then I would expect there to be no nicotine. Now, I do know for sure that if this said that there was 0 tar and there was negative nicotine, that doesn't really make any sense. You can't have a negative amount of something inside of a cigarette in this case. Okay, so on this screen, we went ahead and talked about interpreting slope and y-intercept in context. I'm going to go ahead and go to the next screen, and you'll notice that I still have the same type of situation here. So I still have my graph off to the left-hand side for both the line of best fit and for the residuals. And then I'm going to go ahead and talk about residuals and finding the actual values here. So I think one of the things that we need to do is we need to be able to go back and grab that equation from the previous slide. So let's go ahead and go back there. We're going to go ahead and copy this equation to the next slide. Okay, now that I have my equation copied on this screen, I can now start talking about being able to find, calculate residuals or calculate predicted values. So if we take a look at the question number 3 here, we know that the actual milligrams of nicotine, based off of our graph, we know the nicotine is the Y value. For a cigarette with 21 milligrams of tar is 0.76 milligrams. All right, so if I'm being told that I have actual values here, well, actual means that I am dealing with the real XY. So I'm going to go ahead and write this as a point. So actual, this is my real XY, not my Y hat. It's the actual one. So I know that based off of the values here, the X is going to be the tar. So the tar itself here is 21, comma, the actual nicotine is going to be 0.27. So this is my real X and my real Y. I'm trying to figure out what the residual is going to be. Well, the residual, before I even calculate that, I think I have to figure out what the predicted is first. So I need to find Y hat before I can calculate the residual. Well, that's why I copied my equation over. So what I'm going to do is I'm going to take my Y hat equation, and everywhere I see an X, I'm going to plug in my 21 here, since I know that's what my x value is. So I'm going to go ahead and copy my equation over and plug my 21 in. Okay, so I've got my equation set up now to just copy it off from the left-hand side, and my x value being 21, everywhere I see an x in the equation, I'm going to plug a 21 in, and then I'm going to go ahead and grab my calculator and see what this gives me. And it looks like my y hat, or the predicted y, is going to be 1.519. All right, so now in order to be able to calculate a residual, which is really what I'm looking for here, so I'm trying to figure out what my residual is. In order to do that, residual is going to be the real y value minus the predicted y value. And it is always going to be in that order. Well, I know the real y value since it was given to me. That's 0.27 minus the predicted, which I just found, so 1.519. And I'm going to go ahead and grab my calculator and type that in and see what I get. It gives me a negative, which I expected it to be negative, since the second number than my subtraction problem is going to be bigger. Now the residual doesn't have any type of units on it, it's just a number. So negative 1.249 is my residual for this. Okay, now on question number 4, we want to be able to interpret the residual. In order to do that, when we think about the context here, we already know what the residual value is. It was the negative 1.249 that we calculated on number 3. Now, if the residual is negative, then that means, if we go back to the equation, y minus y hat, that means that the y hat part of it is actually bigger than the real value. So if I were to think about this, so I'll just give myself a quick little sketch here. If I were to think about this, and I've got my line of best fit wherever it may be, what I'm saying is that the real value y is lower than the predicted value of y hat. So the real point is going to be below the line. All right, so I can actually think about it from either the line's perspective or from the point's perspective. So I'm going to think about it from the point's perspective. So what I'm going to say is that the actual amount of nicotine for the, and I want to think about this cigarette specifically. So for the cigarette with 21 milligrams of tar, so the actual amount of nicotine for the cigarette with 21 milligrams of tar is lower than the line of best fit predicts. So what this is saying is the actual y value, so my actual is lower, and I know that because I can even take a look at the sign on my answer from my residuals. If the residual is negative, then the actual point is below the line of best fit. If the residual is positive, then the actual point is actually above the line of best fit. Okay, so moving on to the next slide now, we want to talk about whether when we use the scatter plot and when we use the residual plot, basically. So if we're trying to determine if a linear model is appropriate, we're not going to look at the scatter plot. We're actually going to take a look at the residual plot. So I'm going to go here I'm actually going to take a look at, let's make this a little bit thicker so we can see it. I'm going to look here, but I actually want to take a look at that graph. So linear model appropriate, we care about the residual plot. So when I look at the residual plot, if a linear model is appropriate, I just want it to look like a scattering of points. I don't want to see like a curved pattern to it, or even like a straight line on it. I don't want to see any pattern at all. I want it to just kind of look like a cloud, which I definitely just see a cloud, except for these two little guys on the far left-hand side. I'm a little concerned about those, but I'm not concerned enough to bring it up as an issue. Like, I want it to be perfectly clear. So in this case, I would say, yes, a linear model is appropriate. And my explanation has to do with the residual plot. And I would say it is because there is no apparent or obvious pattern, but I do have to be specific, and I'm going to say in the residual plot. I got two graphs here to take a look at, and I don't want to say I don't see any pattern. Well, we're only talking about the residual plot at this point. Okay, so now I'm going to take a look at the next one. Well, the next one has to do specifically with describe the direction, shape, strength, and possible outliers of the scatter plot. So I'm talking about the scatter plot here, which means I am going to take a look at this guy, and I want to take a look at that graph. So I only care about the scatter plot in this situation. So direction, well, direction is either positive or negative. So are your points trending up or are your points trending down? Well, it looks like my points are trending up. So my direction here is going to be positive, since they are going up. Now the next one that I have is shape. Well, we actually kind of determined that on the first one. Was a linear model appropriate? Yes. So my shape, I would say, is linear. And you can also see, if you look at the scatter plot, it looks like it's forming a line. Strength. Well, strength is going to be how tightly clustered those points are to that line. So the more tightly clustered the points are to the line, so the more linear it looks, I would say it's stronger, and the more cloudy that it looks in the scatter plot, it's going to be weaker. So in this case, they look pretty tightly clustered to me, so I'm going to say strong. And then outliers. Well, outliers, again, from the scatter plot, are going to be things that look like they're not following the trend. So if you take a look back up at the scatter plot, I'll give you an example of what I mean. So something that would be an outlier. So if we look up there, so I'm going to go ahead and put the point in purple so you guys can see it, is if I had a point like down there somewhere. That might be an outlier, or something that doesn't seem to be following the trend. So I'm going to go ahead and get rid of that guy since he doesn't belong there, but I just wanted you to see it. So in this case, outliers, I'd say none. Everything seems to be kind of following the trend of the line. Okay, the last thing we really need to kind of talk about here is the idea of a correlation coefficient, which is R. And it has to do strictly with strength and direction. Now, we will not discuss R at all unless the scatter plot is linear. Now, if it's weak, it's not going to look super linear, but we don't use R for anything else. So if it's curved, it's like obviously curved, we don't use R. It doesn't apply. It has nothing to do with the situation. So in this case, we've got some points that we need to put on. So I've got some graphs kind of set up here for you. And we're going to take a look at, we're going to go from weak to strong. so you see it. But I'm also going to talk about positive and negative. So on the left-hand side, I'm going to deal with my negatives, and then on the right-hand side graphs, I'm going to deal with my positives. So if I have something that's weak, so you can kind of see a linear pattern to it, but it doesn't really have much strength going on. Now on the right-hand side, same idea, it's kind of going up, but it is not strong at all. So in these situations, I would say that my R value is going to be closer to 0, so not super strong at all, and just make sure that the sign is appropriate on it. So over here, this R is definitely going to be a negative number, and I would say it's not super strong, so close to 0. So I don't know, let's do like a 0.3. Whereas this one over here, my R is definitely going to be positive, and in comparison, I would say it's probably as weak as that one. So I'm going to do a positive 0.3. Now it could be a positive 0.2 or positive 0.4. Close to 0, not strong. Okay, so now let's move on to the next one here. So we want to make this one a little bit stronger, but still in the negative direction. So I'm going to take my points, and they're going to be a little bit more tightly clustered, but not a huge amount. So then I've got this one over here. I want it to be a little bit more tightly clustered. So a little bit more tightly clustered and positive. So as we see, we should be able to see that it is a tiny bit stronger than the previous ones. So in this case, my R is still going to be negative since it's pointing down, but I would say that it's probably around like 0.6 or 0.5. So I'm going to go with 0.6, maybe even 0.7. And then this R, in comparison to the negative one, let's see, they're probably about the same, but it's going to be a positive 0.6 since pointing up. All right, so now the one that would be the strongest, or something that is stronger. We want it to be negative, but we want them to be more tightly clustered around that line. So notice that it looks like it's getting closer and closer and closer to what would be like a linear shape. So definitely stronger than the previous ones. So now when our R is closer to positive 1 or negative 1, then that means that it is stronger or more linear. So now this is negative since it's definitely pointing down, and I would say that this is probably at a 0.9 or negative 0.9. Whereas this one over here, I would say is a positive since it's pointing up, and I would say that it's probably about as strong. And then that finishes our video here for linear regression.